Hello and welcome to lesson 9 in the Forces topic. In this lesson we're going to be looking at velocity time graphs. A couple of lessons ago we will have looked at distance time graphs, so it's a follow on from there. My name is Mr. Pratt, Director of Science. The usual, you're going to need pen, paper or an exercise book, a calculator. Got a few calculations to do involving acceleration in this lesson. And unless you're needing to watch this video on your mobile phone, get it on silent, get it out of the way, and try and avoid as many distractions as you can. Straight into the starter then. I want you to explain in as much detail as you can how the motion of a parachutist changes due to the force on her from the moment that she jumps out of the plane to the moment that she lands. So it's from the instant that she steps out to the instant that she touches down on the ground. I'll give you 2 minutes, but as much detail as you can. Just coming up to halfway through your time. Just be finishing off. Okay, you will have done well if you've got all this detail, but anything that you've got that links up to what I've got, just give it a tick and then we'll see how well you've got on. So to start off with, the moment that she steps out of the plane, her velocity, a vertical velocity up and down, is 0 the instant that she steps out. Then the velocity will start to increase, so she'll accelerate because gravity is greater than air resistance. So if you were to draw a free body diagram, you'd have an arrow for gravity pointing down from her centre of mass that's bigger than the arrow pointing up, so she'd accelerate. This velocity will keep increasing then, but the rate of this increase will go down because air resistance is increasing. So the faster she's going, the air resistance is increasing until she reaches terminal velocity. And at terminal velocity, means end speed, the air resistance will be equal and opposite to gravity, so you'll then end up with a steady speed. Some point, preferably before she hits the ground, she'll open the parachute up. Opening that parachute up then will suddenly give a very large increase in the air resistance upwards, so that'll lower her speed. So then she'll reach a new lower speed. It'll still be a steady speed, but it'll be much lower. And then as she hits the ground, you get this very quick deceleration. Very quickly, her velocity will reduce to 0. So if you've got 3 or 4 of those points there, well done, that's great. Let's look at the outcomes then. First outcome, we did describe the movement of an object shown on a velocity time graph. So a few lessons ago we looked at distance time graphs, so it's a step up from there. We just need to be careful that we don't confuse the two. And then from the velocity time graph, for the other outcome, we're going to calculate an acceleration. Now, if you're just doing the foundation paper, it's a straightforward calculation. If you're doing a higher paper, it may involve using a tangent before you can get a gradient. A quick reminder then of vectors and scalars. We've looked at velocity before. I often think in my head or write the word velocity with that arrow there, just indicating to me that velocity is a vector. Speed is its scalar equivalent. So with velocity, it has a magnitude and a direction. We've got to mark it with an arrow. We've got to say which way that velocity is. But with speed, it just has a number. It just has a magnitude. So we might say 15 meters per second, and we're not bothered about the direction that is. Acceleration then is also a vector. So acceleration has got magnitude and direction. But this time, whether it's a plus or whether it's a minus, will tell you whether it's speeding up. So if it's a positive number, like 10 meters per second squared, it means that the velocity is increasing by 10 meters per second every second. So that's a positive acceleration. And negative acceleration means that the velocity is going down. So you could have an acceleration of minus 2 meters per second, which means every second the velocity is decreased by 2. It's gone down by 2. Equation to calculate acceleration, then it's the change in the velocity divided by the time that change is taken. The change in velocity is the same units as velocity, it's just meters per second. We measure time in seconds, which gives us the acceleration of meters per second squared, which is a little bit weird. I'd quite like you to get it clear in your head what that means, because it'll help you understand acceleration. So if we've got a girl, she's standing still, and then a second later she's walking at 2 meters per second, then the velocity has gone up from 0 to 2 meters per second in 1 second. This means she's got an acceleration of 2 meters per second squared, or meters per second per second. Every second she's going 2 meters per second faster than she was before. That's what that means. So her speed increases by 2 meters per second every second. So at 10 seconds, she'd have a velocity of, well, it'd be 2, and then another 2, another 2, another 2, another 2. So it'd be 10 meters per second squared. Sorry, 10 meters per second. So I'll give you 2 minutes just to do these two. Use the equation that's written at the top. So acceleration is change in velocity over time taken. So number 1, number 2, 2 minutes. Just a minute left. Just be finishing off then. So just before we go over them, I've annotated on the screen there. I always will do this when I'm doing an exam question, mark the numbers. So for question 1, we've got the speed going from 0 to 10. So the change in velocity is 10 minus 0. And it takes the time of 5 seconds. And for the second one, we know that the end velocity that it goes up to is 500 meters per second. And we know that it takes 10 seconds. You need to be a little bit careful there. You need to get your change in your velocity from there. Now the change in the velocity, it's going from takeoff, so it's going to start off at 0. So again, it'll be 500 minus the 0. Right, let's mark it then. So for number 1, the change in velocity is 10 minus 0 divided by the time, which is 5, which gives you 10 divided by 5, which gives you 2. Don't forget the units, meters per second squared. So that means every second it's going 2 meters per second faster than it was before. Number 2, find the acceleration of a rocket. So it's going from 0 to 500 and it's taking 10 seconds. So the change in velocity is 500 minus 0. The time is 10 seconds, which gives you 500 divided by 10, which gives you 50 meters per second squared. Well done if you've got those. Let's have a look at a slightly more difficult example. So this time we've got a car that's slowing down as it approaches a speed camera. Speed drops from 34 meters per second, which is about 70 miles an hour, to 20 meters per second in a time of 2.1 seconds. So I want you to find the acceleration and make sure that you've got the unit. Just give you 1 minute. Finishing off. Right, so you've got on. A question like this would be worth 4 marks in the exam. So first of all, let's find the change in velocity. So that's the final velocity minus the start velocity. So it's going from 34 to 20. So it's going 20 minus 34, so you're going to end up with a minus value there, and that's because you're going to end up with a minus acceleration because it's slowing down. So we get minus 14, so the change in velocity is minus 14 and you get 1 mark for doing that. Then substitute in, so the acceleration is the change in the velocity, so minus 14 divided by the time, 2.1 seconds, which gives you an acceleration of minus 6.7 to 2 significant figures, meters per second squared. Well done if you've got that. Let me talk you through now velocity time graphs, then we'll do some examples and then I'll give you some to do yourself. So we have time on the bottom, on the x-axis, velocity meters per second on the y-axis. I've put 0 there, we'll have that as the origin. I've popped on a time of 0 to 12 seconds there and a velocity from 0 to 90 meters per second. Example 1 then, let's have a look at Mike. That's Mike. So a velocity time graph for Mike's journey. It's not very interesting because Mike's not moving, so we'll end up with Mike staying at a velocity of 0 meters per second for the full 12 seconds. So Mike's stationary, he's not moving. Ethel, example number 2. There's Ethel down the slide. So here we have a horizontal line that stays at 2. What is that 2 that it's staying at? Well, it's 2 meters per second. Always use the label that's on the axis. So it's not stuck in one place, it's stuck at 2 meters per second. So Ethel is traveling at a constant velocity there, a constant velocity of 2 meters per second. So it stays at 2 meters per second. There's no acceleration, just a velocity of 2 meters per second. Killer's back. So to start with, Killer is travelling at a constant velocity of 1.2 meters per second, and Killer does that for 2 seconds. Then at 2 seconds, Killer starts slowing down, decelerating, and Killer goes from 1.2 meters per second to 0 meters per second. So Killer stops, so decelerates to a stop, and then stays at a speed of 0 for a further 1.5 seconds. So we've got a steady speed, a deceleration or negative acceleration, and then a speed of 0, so stationary at the end. Thanks, Killer. Progress check for you then. I'll give you 2 minutes, and I want you to describe the motion A, B and C, and then calculate the acceleration just at A, just at that initial slope. Just use the equation, so acceleration is change in velocity over time taken, and do it from there. Don't forget your unit. So 2 minutes. Halfway through your time. Just be finishing off. Question 1 then. Describe the motion shown by velocity time graphs at A, B and C. So A, it's going from 0 to 30 meters per second in 2 seconds. So it's speeding up or accelerating. At B, line is flat, so the line stays at 30 meters per second. So it's a constant speed of 30 meters per second for 3 seconds. And C, now it's speeding up from 30. So if I just mark that there, so it's going from 30 up to 50. So 30 to 50, it's going up by 20 meters per second, and it's taking 3 seconds to do it. Calculating the acceleration at A. So acceleration is changing velocity over time taken. So it goes from 0 to 30. So 30 minus 0, and that's divided by 2 seconds. So it's 30 divided by 2. So it's 15. Don't forget the units, meters per second squared. Gradient of velocity time graph then. A straight line, it's got a constant gradient. And in maths, you talk about the gradient being the change in y over the change in x. So it's the amount it's gone up divided by the amount it's gone across. The change in y there is from 0 to 90. And the change in x is from 0 to 9 seconds, which gives you a value of 10. And it's 10 meters per second squared. So that gradient is acceleration. It is the same thing. You cast your minds back to the lesson we did on distance time graphs. The gradient of a distance time graph is the same as the velocity. Now, the gradient of a velocity time graph is the same as the acceleration. We talked then about acceleration as a vector, so let's see what that would look like on a velocity time graph. Well, we've got an object going from 0 to 90 meters per second in 3 seconds, and it's going at a steady speed, and then we've got that line coming back. So the constant velocity, the steady speed is the easiest bit. So it stays at 90 meters per second for 4 seconds. So it's got a steady speed at 90 meters per second. There, about 200 miles an hour. And the slope there, the acceleration is the change in velocity, that's 90, divided by the time, that's 3. So the acceleration there is 30 meters per second squared. So every second it's going 30 meters per second faster than it was before. Now on that line where it comes down, the change in velocity this time is 0 minus 90. It gives you minus 90. So the acceleration is minus 90 divided by 3, which gives you minus 30 meters per second squared. All that means is the object now is slowing down by 30 meters per second every second. So it's a negative acceleration. You call it deceleration if you want, but it's a negative acceleration. A negative acceleration just means that the object is slowing down. Now, I want you to sketch a velocity time graph for A, something that's stationary, B, something with constant velocity, C, constant velocity again, but faster than B, D, I want you to do constant velocity, but slower than B, E, acceleration, and F, deceleration, which, as we've just said, is negative acceleration. 2 minutes. First line then, no movement, stationary, so we've got to have a velocity of 0. So it'll stay right along the x-axis there, so it stays at 0 meters per second. Constant velocity, so any horizontal line, doesn't matter where you've put it, still right, so that's a constant velocity. For C then, we want a constant velocity that's faster, so it needs to be higher. So C is just higher than B. D, we're going to have another horizontal line, but it needs to be lower than B because it's a slower speed this time. E, acceleration, all we need is some sort of line that's going up. Doesn't matter where you start it from, it doesn't even have to be straight, but that, the velocity is increasing. F, decelerating or negative acceleration, we need to have a line that's going down, the velocity needs to be dropping. Well done if you've got all those right. If you're absolutely positive that you're doing foundation tier, you won't have to do this calculation on distance travelled using a velocity time graph. If you're doing higher or if you're not sure, then carry on. Rest of you can fast forward a little bit. So we've got a graph there, velocity time graph. It's speeding up, then it stays at 8 meters per second, and then it slows down. But we can use that graph to calculate the distance travelled. Velocity is distance over time. So if we look at that graph for the motion between 4 and 7 seconds, the flat bit where we've got 0 acceleration, it's staying at a constant velocity of 8 meters per second. So there at the top, it's going 8 meters per second. For 3 seconds. So this bit here is 8 meters per second for 3 seconds. If the object moves 8 meters per second for 3 seconds, then we can see how far it's travelled. 8 meters per second for 3 seconds means it's gone 8 times 3, 24 meters. So it's gone 24 meters. Because distance is velocity times time. That 24 meters you can also find by finding the area under that line that we just talked about. So if we look at that area, so I've just turned it into a rectangle. Area of a rectangle is base times height, so that's 8 times 3, which is 24 meters. So the area underneath that line there has told us that it's travelled 24 meters in those 3 seconds. The area under a velocity time graph is the distance travelled. So we know the gradient is acceleration and the area underneath the line is the distance travelled. So what I want you to do now is to calculate the total distance travelled between 0 and 10 seconds. Now we've got the middle bit, we've got the purple rectangle that I've done there, and we know that's 24 meters. What I want you to do is to find the other 2 bits of the journey and find the total distance travelled. 2 minutes. Okay, so we've got the middle bit, that's done. So we've got 24 meters for that middle section, we've got that. Let's look between 0 and 4 seconds then, that bit where it's accelerating, that positive acceleration. Between 0 and 4 seconds gives us a triangle. We need the area underneath the triangle. Area of a triangle is half base times height. So the triangle we've got, half, times the base, which is 4 seconds, times the height, which is 8 meters per second, gives us 16 meters. So between 0 and 4 seconds, we travel 16 meters. Middle bit we've already done. That's area 8 times 3, 24 meters. So we've got that one, which leaves us with the triangle at the end, the negative acceleration. Again, it's a triangle. Area of a triangle is half base times height. 0.5 times 3 seconds times 8 meters per second is 12 meters. We've got 16 meters, 24 meters, 12 meters. Add the whole lot up. It will have travelled a total of 52 meters. You've got to remember that you calculate distance travelled by the area underneath. And you must remember when you're finding the areas of triangles or rectangles to use the numbers from the scales on the graph. Don't get your ruler out and start measuring centimetres. It's already marked. Use the numbers on the graph, otherwise it won't work. Using tangents is also higher tier. Let's make sure that you know what a tangent is. This time we've got a velocity time graph that looks like that. That is showing an object that's accelerating. And the gradient is the same as the acceleration. If you imagine you were walking up that slope, the gradient is going to increase. It will get more difficult to walk up it. So the gradient is increasing and the acceleration is increasing. So that shows an object that's accelerating at an ever increasing rate. If the question said use a tangent, might not even tell you to use a tangent, might expect you to know, to find the acceleration at 7 seconds, what you've got to do is you've got to estimate the slope, estimate the gradient at 7 seconds by drawing the tangent. So you draw your tangent line on, which is about the same slope as that point. Then you can turn that tangent line into a triangle. Gradient of the tangent changing y over changing x. Changing y, so it goes up from 0 to 55. So it increases by 55 meters per second. Then make sure that you're finding the change in x, but just of your triangle that we've marked. So that's going from 4 to 6. So 10 minus 4, so 4 to 10. 10 minus 4 is 6 seconds. So the change in x is 6. So our gradient of that tangent line is 55 divided by 6, which gives you an acceleration of 9.16 to 3 significant figures meters per second squared. That's quite a top end question using that. Possibly grade 7, 8 or a 9 even. I'm going to give you 4 minutes now, and in those 4 minutes there's quite a few marks there. You might need a touch more. If you're struggling for time, just pause it. First bit, you've just got to describe the motion of the car between 0 and 45. Don't do all of it, just to 45 seconds. Part B, find the acceleration in the first 20 seconds. So that's that first sloping line up. And number 3, you've got to calculate the distance for the whole journey shown. So you've got to do triangle, rectangle, triangle. 4 minutes. Just got a minute left. Just a reminder, if you're absolutely positive you're not doing higher T, you don't need to do part C. Self-assess it then, please. Question A. Describe the motion of the car between 0 and 45 seconds. We've got two bits to talk about. We've got the 0 to 20 seconds, and then we've got the 20 seconds to the 45 seconds. So between 0 and 20 seconds, we've got acceleration. So it's going from 0 to 12 meters per second. Between 20 seconds and 45 seconds, it's got a constant speed of 12 meters per second. So if you've put acceleration for the first bit, constant speed or steady speed for the second bit, you've got both marks. Need to calculate the acceleration then for part B, just for the first 20 seconds. So the velocity is going from 0 up to 12, and it's taking 20 seconds to do it. So the change in velocity is 12 minus 0, divided by 20 seconds, which is 12 divided by 20, which is 0.6 meters per second squared. There's 1 mark there for the unit and 1 mark for 0.6. The higher question then, what we've got to do is to work out our 3 areas. We've got a triangle for the first bit, we've got a rectangle for that bit, and then the last bit is a triangle. So we've got 3 to work out. Area of that first triangle, half base times height, is half times 20 seconds times 12 meters per second, which is 120 meters. So 120 meters for the first bit. Now we've got as rectangle. Area of the rectangle is 25 times 12. That's 300 meters in the middle bit, and then the little triangle at the end. Half base times height, half times 6 goes from 45 to 51. 6 times 12 meters per second, which gives you 36 meters. 1 mark for each of your meters. Add them all up, gives you a total of 456 meters. Absolutely brilliant if you got that right. Well done. Leave you with a summary then. Just got some annotated graphs there. I've not done any calculations on the summary slide, but if you've not recorded any, it's probably a good idea. You could work out the acceleration on the left hand graph there on that red line. You could calculate that, and that would be 3 meters per second. That's how much the velocity is changing divided by 4. So that's 0.75 meters per second squared. Make sure you can describe a graph. If you're doing the higher paper, you might need to draw a tangent to a curved line to work the acceleration out, and possibly to find the distance travelled, which is the area underneath the line. Well done. I'll see you next time for the next lesson on forces. Bye.